Hello, everyone. This is Recoil Spring Team. I'm Ivan Wong.
My name is Shen.
Will Stewart, Akib Hamid.
The purpose of the experiment is to find the most reliable recoil spring for the Breda 92 in its factory weight. We are exploring springs from three different manufacturers: Breda, Jarvis, and Wilson Combat. To test the reliability, we are corroding them and putting them through a fatigue test. Significant equipment we use include the scanning electron microscope, aka the SEM, the metallurgical microscope, the Instrom universal tester, aka the load frame, and the recoil springs that we ordered. The recoil springs were split into three groups. Group A, the control group, Group B, the fatigue group, and Group C, the corrosion group.
One of the tests that was performed on the springs was the fatigue test. In order to test the reliability of the springs, we did 600 repetitions on all the springs using the setup right here. We can see that we have six different holes, which can be depicted by the red dot. The purpose of having six different holes was to move the springs after 100 repetitions to reduce the random error in the values. The purpose of the fatigue test was to let the springs experience a force under the yield strength. This was done to replicate the mechanical loading that the springs experience during their lifetime in the gun. This data was collected and later used for crack density propagation collection. After every 100 repetitions, the free length of the springs was measured. On the left-hand side, we have a video showing how the setup works. We can see how the springs are getting compressed at the same time, and it must be noted that due to the safety hazard, there was a glass screen in front of the springs in case the springs broke in tension and flew towards the data collector. The glass screen was there to protect, and that is one of the reasons why the image is very blurry.
The next set of conditions that we applied to the springs were corroding conditions. We had a mixture of vinegar and salt and a mixture of hydrogen peroxide and salt, and we dunked each of the three springs in the mixtures back and forth on the stirring plate until we saw that a significant amount of corrosion had occurred. The image on the left shows springs in a mixture of hydrogen peroxide on the stirring plate, and the image on the right shows the same beaker after 24 hours of sitting to rest, so you could see all the sediment settling at the bottom there. And we knew that a significant amount of corrosion occurred because the springs decreased in mass by about 25% each.
After the fatigue and corrosion tests were completed, we took the springs and we placed them into the SEM. Using the SEM, we obtained grayscale images at 250x zoom as well as 2500x zoom on the surfaces of each spring. Indicated by the red dot, the first column is the control group. The second column, B, which was our fatigue test, and then the third column, C, which was our corrosion test. The image in the middle, indicated by the red dot again, was Jarvis Group B. That image is a 2500x zoom. We did not save the 250x zoom, which is why the 2500x zoom is replacing it right here. Looking at the images on the right, as indicated by the red dots,
You can see a comparison between the 2000 and 500x zooms. For corrosion, you can clearly see that there is no cracks as seen by the Beretta Group A one on the top. Therefore, corrosion test was not used for crack density analysis. In MATLAB's imaging processing toolbox, the intensity of individual pixels in each image was extracted. Darker pixels with RGB values approaching 0 signified the presence of cracks, while lighter ones with RGB values approaching 255 represented the spring's undeformed surface. By setting an upper limit, we could essentially extract the amount of cracks in an image. This procedure was completed for both Group A and Group B to compare the before and after images. As an example, we have Beretta's image on the left here, indicated by the red dot. As you can see, most of the darker pixels in the image was covered by red, which indicated the amount of crack density there was in that image.
This plot shows some qualitative results that we gathered throughout fatigue testing. It shows the uncompressed free length of each spring at the initial time, after 100 compressions, 200, 300, and so on. In total, Wilson Comet lost a total of 0.27 inches in length, Beretta lost 0.43, and Jarvis lost 0.6.
The crack density in Wilson Combat was minimum at 11.8% compared to the other samples. The change in length for the Wilson Combat springs was also minimum at 0.31 inches. In conclusion, we can say that since Wilson Combat had the least crack density propagation and the minimum decrease in length, it can be concluded that Wilson Combat was the most reliable recoil spring. In terms of errors, there is a delay between the load frame machine actually stopping and the machine stop button being pressed. Because of that, there was an 8% repetition. There were 8% repetitions that were over-compressed according to the theoretical minimum spring length. In order to improve that, we could use automated machine systems that could do multiple repetitions for the fatigue test, decreasing human error.
Another source of error occurred while we were subjecting the springs to corrosion. Part of the springs were sticking out of the top surface of the corroding liquid about a quarter inch. In order to fix that, we could have added more liquid, more hydrogen peroxide and vinegar.
We also had some issues when we tried to analyze the crack density using the MATLAB code. There were some background pixels that were scattered across the entire image that did not really indicate cracks, since they were just single pixels scattered around the images. To fix that, we could introduce some ways to reduce both black and white pixel noises, therefore allowing crack density to be more representative of the image.
Due to limited time with the SEM, we are unable to capture different regions of each spring. Because of this, we had to assume that the crack density at one spot of a spring is representative of the entire spring, which we know from our images is not true. This is sampling error. Another assumption we had to make was that each manufacturer produced consistent springs. For example, we assumed that Group B of Beretta was the same as Group A of Beretta. This is simply impossible. This is also sampling error. A potential solution we have for both these SEM errors is having more samples at more locations with more springs. I want to thank Clarkson University for funding our research. Thank you, Carl Hoover, for being a great advisor. Thank you, Matt Pinkerton, for giving us background information on guns. Thank you, Hubert, for allowing us to use your lab. And thank you, Daniel, for helping us 3D print. And thank you, everyone, for listening.